The diode is our first semiconductor device, and it's a really important one. Every other semiconductor is basically made from combinations of diodes. And here's a picture of a diode that you can buy. This is just a small little glass package, and that distance right there is about 4 millimeters. And inside here, inside here, is a little silicon chip, and it's manufactured to be a diode. So the question is, what is a diode? A diode is something that conducts current in one direction and does not conduct current in the other direction. And the symbol we use for a diode looks like this. It has this big arrow here that points in the direction of the forward current. Now, one way to understand how a diode works is to draw an IV curve for it. So let's draw an IV curve for a diode. If it was a perfect diode made in some unknown technology, what would happen is in the reverse direction, if the voltage across the diode was negative, we'll label the voltage this way. If the voltage across the diode was negative, that is, this terminal was at a higher voltage than this terminal, there would be zero current flowing. And then for any positive voltage, basically the diode would look like a wire. So I can call that's essentially model number 0 of a diode. Now, when we build real diodes, what happens is we don't quite get that perfect behavior. So in particular, if we build a diode out of silicon, we can I'll go to a number 1 model. And a silicon diode actually doesn't conduct to a slight positive voltage, and then it would go up like that, where this is around 0.6 volts. For a lot of simple circuits that we build, this is a pretty good IV model of a diode. Just as a reminder, when we had the IV curve of a resistor IV curve looked something like this. It was a line that went through 0 and had a constant slope. So a diode is a really different kind of device. It's a non-linear device, as we can see from this. Let me move up here, and now we'll go to a next level model that is actually the one I want to talk about most. This is the model of diode that we use most of the time. So I'll call this model number 2. This is the model that you use when you'll simulate circuits or simulate diodes. And we're going to talk about this a little bit more. So when you have a diode, if I gave you a diode like this, and I said, what's the IV curve of it? So what I would do is I would find some sort of box that made voltage for me, a power supply with an adjustment on it, and then I would also have something that read current. So this is an ammeter, and this is a voltage supply. And we hook that up like that. What we're going to do is we're going to generate this IV curve by making actual measurements of I and V. So my first V setting is 0. That gives me this point here. I hope I measure a current of 0. Otherwise, this thing would be generating power, which it's not going to do. And then I turn up the voltage slightly, and what I notice is there's no current. There's no current when it's at 0.1 volts or 0.2 volts. And then when it gets to around 0.6 volts on the diode, here's VD, and here's when the voltage on the diode is around 6 volts, what I notice is the current goes up. So it goes up to 5 milliamps, and then a little bit higher, it goes up to 10 milliamps, like that. And I can plot out all these points along this part of the curve. Now, I go back here, and I change the voltage here to read the other way around, and that means I'm traveling this way on the voltage axis. And what I'll read, my ammeter, will read 0 milliamps. 0, 0, 0, 0, 0. So that I plot in this part of the line here. Now, if I make this voltage really large and really negative, say I make this like minus 50 volts. That's this point here. What happens is I see a really sharp increase in current like that, right there. And it keeps going. And that is called the breakdown. VBR is breakdown. And for silicon diodes, minus 50 volts is a typical value for that. This graph here shows a break in the scale. So this is minus 1 volt, minus 2 volts, and then we go all the way out to 50 volts, minus 50 volts, and that's where the breakdown occurs. And most of the time when we're using diodes, we're using them between plus or minus 1 volt across their terminals. So that's how we know what the IV characteristic of a diode is. And what we can do is actually, for this section of the curve right here, for this part of the curve, I can model this with an equation. And the equation looks like this. This is the IV equation for a diode. So this is sort of like the Ohm's law for a diode. I equals IS, this is a current, times E to the Q, that's the charge on an electron, times V on the diode, that's the voltage on the diode, divided by KT minus 1. K is Boltzmann's constant, and T is the temperature of the device measured in Kelvin. So this equation actually fits this part of this curve for a real diode. It's a fitting curve. We'll look at these constants one at a time. IS is called the saturation current. Saturation current. And for silicon, that's a value of about 10 to the minus 12th amperes, which is 1 picoampere. That's how much IS is. Q is the charge on an electron, and that equals 1.602 times 10 to the minus 19 coulombs. That's Q. VD is the voltage across the diode. K is Boltzmann's constant. That's a small k usually. And that equals 1.38 times 10 to the minus 23 joules per Kelvin. And the last variable is T, and that's the temperature, and that's measured in Kelvin with a big K. Kelvin is the absolute temperature scale, so 0 Kelvin equals minus 273 degrees Celsius. Very, very cold. So this right here is the diode equation. That's the diode IV equation. And it has this exponential shape in it. It has its exponential term in it. But when we look over here, maybe this doesn't look like an exponential curve. You haven't seen a curve like that. But that actually is just a trick of the scale of this drawing. So what I want to do now is I'm going to zoom in really super close right on this origin right here. And we're going to see how this exponential term shows up. And we'll see what the meaning of IS is. I equals IS times E QV over KT minus 1. And here's a close-up. Here's an extreme close-up on the origin of the diode curve. The voltage scale is blown up by about a factor of 10. So here's 1/10 of a volt forward across the diode. And the current scale is super blown up. This is in picoamperes now. So this is in 10 to the minus 12th amperes instead of 10 to the minus 3. And you can see here, this is a more familiar looking exponential curve. And over here, there's a little bit of an offset. There's a little tiny current in the reverse direction when the voltage is negative. And this amount here, that's IS, flowing in the negative direction in the diode. If we look at the diode equation and you let V go negative, what happens is this term here in the diode equation becomes very, very small compared to 1. And what's left is IS times 1. And that's what we're looking at right here. This is a really small current. As you can see from the scale here, it's down in the low picoamps area. Almost all the time you can ignore this current and just treat it as 0. Now I want to use a diode in a circuit, and we'll see how we solve circuits that include these nonlinear diodes in them.